What is up, YouTube? Mr. King coming at you live, not from the studio, but from the classroom today. So you may be hearing some students in the background. What we're learning about today. So first, could you put on your paper atomic stability notes? Okay. And the essential question is, why do big atoms decay naturally? Why do big atoms do that, but not small ones? Okay. So hint. Red Eyes, Black Dragon, and this atom both decay. So I'm going to play a little clip from Yu-Gi-Oh! Of an atom decaying. Okay, so right now, this little clip from Yu-Gi-Oh! The Time Wizard is going to make the dragon decay. So trying to figure out what does decay mean based on this. Okay, based on that, what does decay mean? All right, hopefully you notice decay means to break apart or break down. So radioactive decay is atoms breaking apart. And when they break apart, they release matter, so parts of themselves and energy. That's what radioactive decay is. Decay is breaking apart. Okay? Please write that down. The star means it's important, so write it down. On the other side of your notes, please draw a picture of something decaying. And some review. What are neutrons good for? What are they good for? Remember, the opposites attract. Okay, so what do you think neutrons are good for? Hint, this ref is acting like a neutron. Okay, so neutrons block off the protons and electrons and they stop them from colliding. That's why they're good. So remember, opposites attract. So these protons want to be near the electrons because they behave like magnets. So the neutrons are blocking them and keeping them apart so the atom's stable. So could you write down, the more neutrons, the more stable, because you basically have more peacekeepers or more teachers or more refs trying to break up those fights. So they break up the attraction of the electrons. So that's what the neutrons do. They stop these from attracting and they stop these from repelling. That's why more neutrons can be more stable. So could you draw a picture of this on the right side? Next, I want you to think, we're gonna scale it up a bit. How do you stop a riot? A riot, like in the Joker movie, is just a crazy event where a lot of people are committing violence in the name of a cause. You're the mayor, though. You're in charge of keeping the city safe. So what would you do to stop a riot? Okay, try and think about it. It relates to this. Bigger atoms need more neutrons. And my point was that as atoms get bigger, the protons are harder to control, just like a riot. So you need more neutrons to keep the peace. So like carbon has 6 protons. 6 aggressive people, not too hard to control. But uranium has 92 protons. So that's like 92 aggressive people. So you'll need a lot more neutral people to try and control it. So you'll need a lot more people to help keep the peace. You could have like community members or something that's neutral. Okay? So like this atom, harder to control. There's more going on. These two are easier to control. The next, I have a little activity for you. I want you to get a random piece of paper. Okay? Here's what I want you to do. You need a piece of paper. I want you to do it with me. Get the paper, a paper like this, fold it in half, and then fold it in half again. So you have it in fours. Okay? Write in your notes, how hard was that? How hard was it to get it like this? 1 impossible, 10 super easy. Okay? Next, do it again. Now fold the paper into eighths. So it's this big. How hard was that on a scale of 1 to 10? Then do it again. Now the paper should be in 16ths. How hard was it to fold it like this? 1, nearly impossible. This one took a little more strength, so maybe you could see like a 9. Next one. Try and fold the paper again. So now you folded it 5 times. How hard was it? Write it in your notes. This was probably like a 4. Next one. Fold the paper as much as you can. Okay? Now try and make it this small. How hard was that? Okay? And then try and do it again. And write how hard was that last fold. Okay? Almost 8 times to fold this paper should be almost impossible. Okay? So every fold that you did, write down how hard was it each time. And if you're curious how many times you could fold it, go backwards. It's like 1, 2, 3, 4, 5, 6, 7. Okay, that's how much I was able to fold this paper. So there was a point to that. The world record, if you're curious, is 12. Brittany designed her own paper. Anyways, I want you to think, why was it harder to fold the paper over time? Why was it getting harder? Try and think about it, okay? For example, these pliers are the only thing holding that paper back from folding back to being flat. Why was it getting harder to fold this paper over time? Okay? It has to do with this. Strong nuclear force. Strong nuclear force is how tightly the atom can hold the nucleus together. So a strong force, you really hold the atom together really strong. So strong force means it's very stable. It's held together very well. A weak force, hard to hold together. It's very unstable. You're barely able to hold on to it. That's a weak force. So this atom is very stable. It's really easy to hold that nucleus together. This one, very hard to hold together. I want you to try and pause the video now. How do you think this relates to the paper activity? Okay. Hopefully you guessed that it's harder to hold an atom together when the atom is thick, just like the paper. When the atom, instead of being thick with a bunch of layers of paper, the atom is thick with protons and neutrons. So this atom is a lot harder to hold together compared to this atom. This one is completely stuffed, so it's very hard to control. Whereas this one, there's a lot more space for the atoms to move around, the protons and neutrons to move around, so it's a lot easier to handle. So the thin piece of paper and the thin atom are both very stable. They are held together with a strong force. This thick paper and this huge atom, they are very unstable. They're barely able to hang on together. That was my point. It's just like atoms. So based on that, why do you think carbon with 6 protons and 6 neutrons has a very strong nuclear force, 100 million newtons? That's how strong the nuclear force is. But uranium, a really big atom, has 92 protons and 146 neutrons. Their nuclear force is really weak. So this is hung on to really tight. This one, not very strong at all. Barely able to hold on. Why is uranium's nuclear force so weak? Pause you now, try and think about it. Okay? Hopefully you noticed that big atoms are unstable. They have so many protons and neutrons that it's really hard to keep them together. They just want to break free because there are so many, it's hard to control. That's why the nuclear force is so weak. They're barely able to hold on, whereas smaller atoms have a really strong force. They're really hard to break open. And the reason is because those big atoms, they're stuffed with protons and neutrons, so the force holding them together is very weak. That's why big atoms break apart, because they want to break apart so they can be more stable after. Okay, so last thing in your notes to get points, write a summary saying, today I learned that blank, and give a reason why big atoms, like uranium, break apart and decay naturally or easily. Why are the big atoms the ones that are radioactive? Try and think about it. That's the last thing. Thank you so much, everyone, for staying with me. Have a great day.